Okay, so now we're going to get into the instructions of the KUKA robots. Okay, so basically, I would like to show you some instructions that are available. And the first one that we're going to take a look is the wait instruction that is widely used to set up a waiting time in the cases that we need to make the robot to wait for a few seconds before jumping into the next instruction. Maybe you need it for something specific of the process that the robot is involved in, and then you need to add up a wait instruction for the robot to wait for a specific time before moving to a specific place. One interesting example is in the spot welding process industry, where I can add up a wait time before performing a movement from one welding point to another welding point. Why would I do this? Well, it is very common to have failures in the spot welding process related to the cooling system of the tool. But the immediate and definitive solution for the problem correction would be a complete repair that would take a considerable time, and therefore it will cause a production interruption. So sometimes we can use a wait time if, for example, we have a high temperature in the spot welding tool, we can add a waiting time between spots to let the tool to chill out before going to the next spot and avoiding damaging the production or the robot. And this can be done until lunchtime, for example, if we have the problem in the morning, and then we wait to the shift exchange or some event that could happen in the facilities to allow us perform the repair and does not stop the production for too long. So we can use now the time that it takes to change shifts or the time that it takes to lunch, and the production would be stopped anyway, and we can adapt ourselves to the conditions proposed to reduce the downtime of this production line. So this can be used in a very different situations, and I like to share those experience because in the future, if you guys can face a similar situation, you know how to go in these cases. Okay. So just to recap, the wait instruction means, as you can imagine, a waiting time for the robot. So you specify in the instructions at the attribute of the time you want to wait, 10 seconds, 15 seconds, 1 second, whatever time you want it to wait. And we can add the instruction right here, clicking on commands. In logic, we have here wait, and we also have a wait for instruction. The wait is for a specific time, while the wait for is waiting for something specific, waiting for something to happen, not the time itself, but some attributes that we can select, signals, in which the robot will wait for those signals to have a specific condition before going into the next instruction. So that's the difference, okay? While the wait command, we wait for a specific time, the wait for conditions of digital signals that we receive from the robot. So now if we want to add a wait, we go here in commands, click on logic and wait, and then we add the wait structure, and then we can select the time we want, for example, 5 seconds. So what will happen is that the robot will get the program pointer stuck in this condition, in this instruction line for 5 seconds. So it will wait to pass this 5 seconds before going on and executing the next instructions in the program. Uh, in the next class, we will set up a wait for instruction from scratch, and then we will understand better the difference between those two and when to use one or the other option. So similar to wait time we've seen, we have also the wait for instruction. We've seen the way to add an instruction here, so let's just cancel this one and we go to logic and then go to wait for, and it appears here for us, and we have some options to configure my structure. I can, for example, set a logic not to negate a complete logic sentence. So imagine I have a complete logic sentence, but I want the not result of it. I can do it here. So I can add a not in front of everything, but I have also all these options here where I can change, for example, the information that I need to check in order to ensure for my sentence. So I have inputs, I have outputs, I have cycle flags, I have timers, and I also have flags that I can use in my logics. So I'm configuring here an input 1. I'll click OK. So now I have a wait for instruction with a condition on input 1. So input 1 needs to be true. And so if input 1 is true, the program robot will continue its way. But if not, the robot will remain waiting for the condition to be true so it can continue, okay? Good. Then, so we can understand how this works here. I will come here on the menu. Let me go to IO, so editor, IOs. And here we have our input 1, for example, all right? Now I'm going to set the robot to auto mode. Okay, setting the robot to auto mode. Okay, now I can start my simulation up here. Good. So my program is executing here, it's running, and then note the following. Up there in the message banner, as we have seen in the message system class, we have a pop-up of a status message, and also the counter of messages increased. So basically we have here that the robot is in a waiting state, waiting for a signal to enable the execution or to resume the execution and return normal process. And you can see that the message is clear, aguardar entrada 1, which means waiting input 1 in Portuguese. So we know that the input 1 is 0 and my program pointer is stuck here, or more specific, I need to input 1 to go true to my program to continue execution. So let's do the following. I'm going to set the robot to T1 here first. T1. And I'm going to reset the program. Reset or restart the program. I will put a step selection here. We will see this function later more deeply. Don't worry. And I will select this here. Okay. Click here, start a simulation. For me to start the simulation, I need to be on administrator mode, like that. My password. Okay, so simulation enabled. And I have a condition here now showing me that the robot is in simulation mode. Okay, my signal is in true already. I can now switch to auto mode again. And I can start the program. Now the robot went straight through the wait for instruction, because now the condition of it, which means signal 1, is true. So it continues and then it resumes its operation.
Alright everyone, so now we're going to look at the out function. Basically, it's a digital output. It's used to send signals within your process, right? So imagine the robot is going to mill, for example, then as it approaches the milling point, it needs to send a digital output signal to turn the milling machine, for example, or to activate any other system that's been used, like a blower for air, for example. So usually if you have a system like this, it will be physically connected to the robot's I/O board, okay? But it can also, of course, receive a signal from a PLC or send a signal to a PLC to turn on the milling machine or to automate everything in a more advanced line. But basically, to reference a signal here, we can go to commands, logic, out, and then we have out again. So now we have the instruction. I created a signal already, a digital output with address number 1, and I added a comment, treinamento. So if you have a comment for the signal, it will show here. Now, on this attribute here, we can set the value that we're setting to this digital output. In this case, I'm setting true, so I'm turning it on. And this logic represents if it's continuous or not. Okay, so we can set it to a continuous mode or not. I'll click OK here to locate my command, and I'm setting it to true. So in the menu under displays, digital input and outputs, we can see a digital output here, and we have here our execution mode. So we'll change it to manual first. Okay, now it's on manual, and in this way we can monitor the execution of the program, and we can see that the value was set. So I've set this signal to 1 once the robot passes through that instruction down there. So if I wanted to set it to false, I could change here. So I can use my replace command here and change the value that is setting to false, for example. Now it will deactivate the digital output once the robot go execute this line. So as you can see up there, it's grayed out, so the signal was deactivated. Okay, now let's take a look at the push out command. The difference between push and push out, this was out earlier, is that out is just setting a value. So it will keep that value until we change it again in our program. So imagine that I need to send a signal 1 or 0 for undefined time or until the robot reaches certain conditions. I can use out for it. But push actually will maintain the signal at 1 or 0 for a specific period of time. So we can use the post instruction if you go to commands, logic, out, and post. Here we will specify the address of my signal. This one is associated with this comment do treinamento that we've created earlier. If we don't have any comment, it will be blank. Okay. Here we say the state, if it goes to 1 or if it goes to 0. And here we have the count parameter to continuous or not. But we have another parameter here that's time. And this is the time that the signal will stay at 1 or 0. Okay. So this is the post length. And if I click OK here, let's execute this logic. You see that the signal goes to 1 and it stays at 1. I'm not doing anything here. After 3 seconds, it's off. So that's the pose. Well, there's another output option, and this function works without the regular output. Essentially, it's instruction that allows actually the purpose of using this special output is to integrate a specific output into a trajectory of the robot. So imagine that the robot is executing a movement, and during that motion you pass certain attributes so you can trigger a signal output. The goal here is to avoid interrupting the robot's movement when triggering the signal or triggering it in a very specific place in the space. So there are specific functions in KUKA to address this type of situation, enable signal triggering during a robot's specific movement. For example, we have consider the last case we discussed. The robot moves toward a milling point. As it approaches, we could use an output to activate the milling cutter. But if logic with continuity is placed without the count parameter, this could impact the cycle time. So we can now embed parameters into the movement of the robot, so it triggers the output automatically as it comes toward the milling point. So this optimizes the process efficiently by integrating the signal into the movement. The robot ensures the milling cutter is ready only when needed. Once those parameters are met, the signal is triggered, and the milling cutter activates at full speed just at the moment when the robot arrives at a specific point. Um, so this is a very useful for optimal operation. And the idea is to signal an output command operator in this interface here. So we have this instruction here called syn out. Okay, so we have syn out. This instruction shows the target memory address here, 1, that has a comment do treinamento. So we have this output 1 with this symbolic. Okay, this command always must follow a movement instruction to do this. So proper synchronization with the robot's movement. Here you say if going to true or false, and this section will define when this movement shall happen, and at the start of the movement, at the end of the movement, for example, or during a specific path. We will see how this happens primarily. And in delay, we can determine an offset. For example, wait until 20 milliseconds passed since you passed this specific point. Two scenarios here to demonstrate how this works. Okay. First example, we have a non-output operator here. So observe the robot executing those sequential points. So we move from point 1 to point 2, then to 3, then to 4, and go on. Okay, it continues the motion. Notice that we have linear movements here. So linear movement to P1, linear movement to P2. Then we have the syn out with the comment signal 8 passing through to its output, triggering at the start of the movement the output. So we said start here, and with a 20 millisecond activation delay. Then proceeds to point 3 and point 4. So robot moves to point 1 here, following the instruction. Okay, robot moves to point 1, moves to point 2, and as I mentioned earlier, this command must link to a motion. So using P2 as a reference position here, during P2 execution, actually, the trigger at the start will be programmed with a 20 milliseconds delay. So after this delay period, signal 1 initiates milling cutter operation, okay, or activates any system. So it will be automatically output at this specific point when the robot leaves the point 2 position, because we have the syn out here and we have before the P2, so the robot will be in P2. And when we say, okay, at the start of the movement to P2 to P3, okay, at the start of the next line movement, the linear to P3, you will automatically trigger at the start of this movement waiting 20 milliseconds. So that's what happened. Another example here, using continuous mode with zone parameters here. So you can see these motion features has been adapted here, blended paths, okay. So we have those transitions of the robot from point 1 using approximation or continuous movement. It will have this angular tolerance here for smooth point-to-point transitions. During motion from P1 to P2, the system calculates transitioning to P3. It's triggered here at the start, okay, with a 10 milliseconds delay. So once the movement from P2 to point 3 starts, it will wait 10 milliseconds, and then the output will be set automatically. Okay, the P3 trajectory endpoint is here. So another example here shows us a negative delay implementation. So we have the point 1 to point 2, and then with linear logic, and we have linked to point 3 here as a reference. So as the robot approaches point 3, it presses a minus 20 milliseconds activation delay. This means 20 milliseconds before reaching the point 3, the system activates signal 9. So we can use negative delays here if we want the reference to be to the arriving point. If we use positive delay, then we are referencing the start of the movement, not here the end of the movement. Okay. One possibility is to use also the path parameter. The path parameter is compatible with linear or circular movements only. Point to point is not compatible. And this happens because in path we define a path in millimeters. So imagine this case where we move to point 1, then we should move to point 2. But between those movements we have this output with a minus 5 milliseconds delay here. But the sequence continues to point 3 and then point 4. Okay, so this command outputs to the output 9. We have it to 1 with a 20 millimeters path and a delay of minus 5 milliseconds. What happens in this case? So we have movement to point 1 here first, okay, and then before going to point 2 we have the sin out, but the sin out is configured minus 5 milliseconds. This means that the reference should be from point 2 here, but we have an additional path of 20 millimeters to be used as a reference point because we have specified this here, okay? And we also have a minus 5 milliseconds delay. So what happens is we add 20 millimeters to the trajectory where the reference point should be, and this is here, and then we consider the delay here. So this increases the path from the reference point. So point 2 plus 20 millimeters, and then from this point on we wait until it misses minus 5 milliseconds for us to get there. So this for miling is very precisely for miling processes. And before engaging to phase 3 or phase 4, we will ensure that the output is set at minus 5 milliseconds away from 20 millimeters point after point 2. This, for process synchronization, for precise miling operations or any other precise operations, is fantastic. But a key consideration, as we start to using multiple things like that, we have a more complex software and hard to understand. So always stick to basics, okay? So if you can handle a situation with regular outputs, linear movements, and just regular stuff, that's easier. Because if you're programming those complex things, you know you can see the trajectory in your head, and this is clear for you. But this is clear for you that's developing the application based on a movement that you already know. Someone that doesn't know the movement and is looking at the program should be hard to understand all those parameters here referring to an imaginary point in space. So always stick to basics and use this if you need it. So this 20 millimeter path, minus 5 milliseconds, some things like that can be used in some real scenarios, in some more complex scenarios, but if possible, stick to basics, and this will probably be enough for you. Okay, but this is a very important feature, and it allows us for precise synchronization with movements. Okay, we've looked at function sin out here, and through some examples we've understood how it works. It always related to the movement, so it will always exist in this form. We have a movement, and then I have the sin out within movement, so you have the instructions here. We've discussed the path, we talked about delay, and we also talked about the signal states. Another command that we have, another possibility, is use the sin pulse. Its functionality is essentially the same as the sin out, so it's a synchronized output, but we use the pulse behavior, so it generates a pulse on the output. It's essentially the same thing, so let me add it here. It has the same instruction as the sin out. I'll click OK. So you can see the structure is exactly the same. It pulses output 1, which is the training, for 3 seconds. and with a path of 10 millimeters and a delay of 0 milliseconds. So the structure itself is the same. The only difference between them is that it pulses the output. It generates a pulse instead of setting the signal to 1 or to 0 permanently. Okay? Okay, so now let's see how can we create and view variables in the controller. Local variables, we're saying here, okay? So first, KUKA system requires that the local variables can only be created in a module if this module is not active or not selected. So we need to ensure that the pointer is not inside the module during the insertion of the variable, okay? So what happens if I try to create a variable here? Let's see. Go to commands, and here we have in logic the option declare variable. So this is the option we use to declare variables, but if I click, command is not allowed for a selected module. So if my module is selected, I cannot insert a new variable to it. So to do this, we need to deactivate this module. So come here and cancel the program execution. Now the module is nice for us to click on open, so we can open it in edition mode. And now we can go to commands, declare variable, and then we have the option here to define the type of the variable, integer, boolean, or real, floating point, or decimal. Let's create an integer. Let's name it train var for training variable in Portuguese. Okay, so click OK, enter, and now we can click on command OK, and it says that the data file will be changed, and if I close my src file, it will be changed automatically. And he wishes me track. Okay, yes. Okay, now we have the declaration of our variable here added into this local globe. The data variable now contains all the parameters here that we need to use it inside this module. Okay, so this is a local variable, and we can only use it inside this module over here. We cannot access its values from another module. For accessing variables in all modules, so we can have a proper system-wide availability of a variable, so it can be accessed from all modules, we need to declare a global variable. And this should be done at the config data file or the machine data file, which are system files. So when using global variables, we need to edit those system files, and this is something that you need to consider if it is worth doing, or if you don't have a different way on doing this. Okay, so remember, all the variables that we declare inside a module are available only to be used for this specific module. Okay, so now let's see how our program executes. I'll go back to the navigator here, and let me select my module. Actually, let me go back to the editor. I need to close the editor first. Okay, now I can click here and select my module. And once I've done this, now I have our program pointer here. But how can we see the value of our variable? We can click here on the manipulator icon again to check this variable. Click on view variable individual, and then here we can select or enter the name of our variable, train var. Enter. And so here we have an interface to manipulate and monitor the value of a variable. So we have a debug window basically to to see the value our variable gets, so here we can see the actual value of the variable, we can monitor the actual value of this variable during the program execution. And here we can also insert a new value. So here I selected 0, and if I click here on set value, you can see that the actual value goes to 0. So we have also an option to set values. So if I go to 1, click on set, this actual value goes to 1. And notice that we always need to, for monitoring this, we can use this feature over here. Always we need to specify the module. So we're dealing with local variables, so we need to say which module are we looking into. So here we need to select the module also. In addition to the variables that we can create and use in our programs, there are also system variables that are inside variables of the KUKA systems to store information like the home position or the current robot's position and other things or other information. Whenever you use a dollar sign, it will represent a system variable. So here, if I say, if I place a dollar sign here, and then I click, I type pos act or actual position. So this information returns the current position of the robot, the actual position of the robot, including the X, Y, Z, and the ABC angles, along with other details as mentioned earlier. We've discussed the position variables used in KUKA robots. Here we have the position, how to check the system values of the robots. Remember, the robots manual lists all available system variables that you can use in your programs. Those variables help to analyze data and monitor the robot's current state. You can use them to debug or to validate a specific system condition before going to a next step.